So we are doing design practice 5, and if you haven't read design practice 5, the entire script, I think you should take a minute and do so now before continuing with the video. Alright, so for those of you who read, I will explain what is happening. Here we have a rig that is proposed, and we're using this proposed rig to actually test the strength of bolts. So what we have a vertical member here, we have a pivot in the center, and we have a mass at one end, and we have the bolt that we want to test the failure on the next end. So as we load up with different masses here, it will apply a force on this end through the lever arm, and eventually it would snap, will fail the bolt and shear. Right, so we're saying that for the lever, which is what we want to design in this exercise, if we use a normal 1020 steel, and that is has sigma yield of 270 and modulus of elasticity 200 gigapascals, and due to the space constraints, right, how the size of this thing must be no less than 1 meter, meaning that A plus B, the entire length should be no greater than 1 meter. So you could already see that we have a constraint here in our design optimization. In order to fill an M5 bolt with a 12.9 grade, so that's the maximum bolt size we're looking at testing, we want to be able to use a 50 kilogram weight. So at 50 kilograms, we should be able to fill an M5 12.9 grade bolt here. So the different task is to do the following calculations parametrically, meaning that we're doing it by letters. We're saying T and H and F and L and A and etc. We're not putting any numbers to it as it. Determine the force F2 required to fill our fastener. Right, so we know that the shear force in the bolt will be equal to, in order for failure, we will assume that the shear force in the bolt has to be equal to the ultimate shear stress. Right, so what that is here, we say the ultimate shear stress of the material. So you go to the tables in the handout, and you get the ultimate tensile stress for 12.9 grade material bolt. Divided by 2, and that will give us the ultimate shear stress. Right, that is the assumption we're making, and we say that if the shear stress in the bolt is equal to or greater than this shear stress, we will have the failure we want. Right, so based on an M5, we could actually go to the notes again and get the area for an M5 bolt, the shear stress area. We have the maximum shear stress that the bolt could withstand before failure, so you could actually calculate the force F2 to fail. So that's what we're doing here. Right, so you're doing this parametrically, meaning that we're leaving it as sigma ultimate, AR, F2, etc. The next thing is to sketch a shear force and bending moment diagram. However, before I go on to that, we know that we have a lever arm system here, right? And that our 50 kilograms must be able to give us that F2 that we calculated here. Right, so you could see already now that we have another constraint where using 50 kilograms or 50 times G should be able to give us enough force through the lever to give us that F2 we calculated here. So that will be another constraint. So you could see we already have two constraints. We have A plus B is equal to 1, and then we have a constraint where, given the dimensions of our lever arm, 50 times G could give us F2 on this end here. The next step is to sketch the shear force and bending moment diagram of the lever arm when the rig is in use. Right, so this is a simply supported beam, more or less with a load in the middle. So this is simple to do. So you sketch it, and again, you can leave it in terms of F1, F2, A, and B. For a rectangular cross section of height h and thickness, determine the maximum shear stress. Right, so that maximum shear stress is your tau max. Right, so that will be your tau max value that we calculate. You can recall that tau max right, so this is our tau max value they're asking to calculate. right? So that tau max again is your sigma bending and your tau xy. You're getting that from your shear stress, your shear force, and a bending moment diagram, which you have been doing throughout the semester. And then next is determine the maximum deflection in the lever arm. So you go to tables online to determine what is the maximum deflection formula. Right? Again, if you look at this, we have a beam, we have a load on it, and we have, right? So if you turn the lever upside down, it will look like this. Right? So you have a deflection, and you have A, you have B, so you could go online and find the formula for the maximum deflection. So as you finish these equations, you have it in parametric form for these 4 equations. You come to an Excel sheet, right? And this is how your Excel sheet could be arranged. You have your inputs, you have your variables, equations, constraints. Right, so your input will be sigma yp, the area. This is from your table for the M5 bolt, the sigma ultimate from your bolt. And in here now, F1 and F2, you will have your equations. Of course, F1 will be 50 times 9.81, which is the weight on one side, and you have the equation for F2, right? You have E, L. Now, A, B, T, H, and N. Y also. We don't know these things, right? So we could just input these starter values for now, right? So again, in this side here, I converted it to millimeters, so you could just have a visual of it, right? So this is 0.5 meters, but it's really 500 millimeters, right? So you're using these initial values now to test your Excel sheet going forward. These are equations, so this would be your I, right? Again, this is TH cube on 12 for your I. You have your area, then you have your tau max calculation, right? Your delta max calculation. Again, this is from your formula for the table that you will have got. Well, the formula for delta max or your deflection for that particular system. And then we throw in 2 other equations here, which is A divided by B and A plus B. Right? We know that A plus B should total to 1. Right? So what I could do here is just make this numbers is general. So you will see, so A over B is 1, A plus B is 1. Right? And then constraints at the end here will be the A divided by B you recommended, and we'll talk about this just now, what our constraints are. Right? So at this point, what you could do is pause the video and complete the questions 1 to 4. Those are these 4 questions, so that you'll be able to complete this table. Right? And you could actually test it with these inputs and ensure that your values are in sync with what we got here in orange. Right? So everything with orange in it is an equation. Right, so once you have the sheet working and you have your formulas for F1, F2, you have all the formulas for I, tau max, etc. Now we can move on to the actual optimization part. So as right now we have unknowns. We don't know what A is, we don't know what B is, we don't know what T is, we don't know what H is, we don't know what N is. Right? So we just don't know any variables right now. So if we wanted to solve this by hand, then it would be almost impossible. So that's why we're going to ask Excel to get the best parameters that will meet all our constraints. And our constraints are given in the constraint table for the solver parameters. Alright, so let's talk about the constraints. And well, one in particular, right, is this paragraph here. We say that sometimes if we design a component and it's within our stress limits, meaning that tau max is less than tau design, we so far had stopped there in our design because stress-wise everything was good, right? But if we could have a situation where we could have deflection happening, so even though it's safe and the stress is not there, we could have it sagging too much, and that might be unacceptable based on the design or the tolerance, etc. Right? So one such guideline, design guideline, is, for example, for every meter of machine we have, the acceptable deflection is 0.5 millimeters. Right, so if you have a component that has a rod, for example, and is 1 meter long, then an acceptable deflection is 0.5 millimeters. If it's 2 meters long, then an acceptable deflection will be 1 millimeter. Right, so for every 1 meter of machine, the deflection should be 0.5 millimeters for it to be acceptable. So we need to factor in this guideline now into the overall design constraints. Right, so we go to the solver and solve a winner just like we did in design practice 4. And we said, okay, our objective is we want to have our second moment of area, that's of the cross section. We want to minimize it, meaning that we want the smallest permissible section of it. Right, so this is our cross section. Right, we want Excel to make this as small as possible because we don't want it too big. Right, so we put, in order to maximize this, we use second moment of area. We could have also used area, normal area, but we use second moment of area because it's more tied to the bending stress, the second moment of area, than it is normal area. So we put second moment of area, and then we want to set it to min. So we asking Excel to minimize it. And how are we going to, what Excel is going to change? Well, Excel could change A, dimension B, it could change the thickness, it could change H, it could change the factor of safety. So those are the things we want Excel to change. Right? But we must follow the rules or the constraints. So we say H should be greater than T. Of course, it's a rectangular cross section in the vertical sense, so we want H to be greater than T. Right? The N must be greater than or equal to 2. So we want our factor of safety greater than 2 in this case. Our tau max, of course, must be equal to tau design. Our delta max, which we calculated in number 4 here, right? That is given from a formula for a simply supported beam. That must be equal to the recommended. And what is the recommended? The recommended is A plus B. So I'll write that here. The recommended will be A plus B, because that's the total length, multiplied by 0.0005. That'll be another 0 and then 5. Right? Because it's 0.5 millimeters. Take off one of the. Right? So it's 0.5 millimeters. So the recommended here is A plus B multiplied by 0.0005 meters. Right, so whatever A and B works out to be, when we add it, we multiply it by the guideline here. And we say that that deflection must not cross that. The next thing is that remember we have, when you had worked out between F1 and F2, we have a ratio of A to B is equal to F2 and F1. This is our lever arm equation. Right? So the left hand side is equal to the right hand side in terms of moments. So that is this constraint that at the end of the day, the machine or the lever must conform to the physics of the lever. And then finally, A plus B is equal to L, where L is equal to our maximum, which is 1. Alright, so onto our solver, let's look at the constraints equations. You could see for A plus B, the formula will actually be F2 divided by F1. Your recommended will be A plus B multiplied by what our recommended was, which was 0.0005 as indicated before. Our tau design, well, is our sigma y p on 2n. And our L, well, this is our constraint. The question said that it shouldn't be greater than 1 meter. So now we could actually put all this now as we have in the solver parameter box, and we could actually work this out. So again, we go to data, solver, and we have our solver parameters. So we said again we want to minimize our Sakamoto area, which is this cell here. Right, we want to minimize it, so we click minimize, and we want to do that by changing A, B, T, H, and N. So you notice when doing this, what we want to change, we can normally put it one after the next. That's just like in design practice 4. So it'll be easy just to drag down. So we want to change A, B, the thickness, the height, and the factor of safety. Right, so our rules, as highlighted before, right, you could follow along. The first thing is that H must be greater than or equal to T. So we could say H greater than or equal to T. The next is the factor of safety. We said the factor of safety, N, must be greater than or equal to 2. And finally, well, not finally, we have 2 more. So it was our tau max must be less than or equal to tau design. Alright, so we will just make it equal to. So our tau max should be equal to our tau design. Right. The next was our deflection. So our deflection must be equal to our constraint deflection. Next is A over B is equal to F2 and F1. So A over B must be equal to our constraint here. And 5 plus B equal to L. Alright, so we have what we need to the input. We have our Sakamoto moment of area. We tell in Excel we want to minimize that so they get the smallest possible section. We want to be able to change, want Excel to change all the lengths, A, B, thickness, height, and factor of safety of the beam. And these are our rules, our constraints. Right, so at this point we could click solve. And you could see here that we have a solution. So we have A is 943, B is 56 millimeters. T and H, you notice, is 44 and 44, so it's given us a square solution. Alright, so if you go back to the solver, I'll just go back here. We said that H must be greater than T, but in reality, we cannot get greater. We got greater than or equal to, so it actually took the equal to more over the greater than. Right, and our factor of safety is 8, so we have a really high factor of safety, which is over designing too much. Right, so what we could do is we could click restore original values here. Make sure we turn the solver parameter. So when you click OK, what it does, it reverts back and brings it back to the screen. So what we could do now is we could actually now modify our factor safety constraint. Because we have greater than or equal to 2, it will take any value once it's greater than 2. So that's why we got that large 8. So we could change this and make it equal to 2. So we could confine it to 2. So if we were to solve this now, you could see we actually get some values that make a little more sense, where we have thickness is just 1.3 millimeters and our height now is 140 and our factor of safety is 2. Right, if you look at our tau max is 67.5 megapascals and our tau design is 67.5. So it is on the brink of the stress of the material. So we maximizing then the material itself. We have A and B. When A and B is added, we would get 1. Right, so A and B is 1. You could see the remain as 1. And we have our ratio of F2 to F1, which means that we would get our force that is required at the end of it. A and B, or A over B must maintain this ratio of 16.66 in order to get our force at the end. Right, and we could see that we maintain that ratio. So what this means is that this design is actually good and we could use the thickness. We could increase the thickness if we want a little more. Right, just to make sure. We could also go back now and manipulate. We could actually put a constraint on the thickness where it cannot be less than 5 millimeters, or the height shouldn't be this high, it should be less than 100 millimeters. So you could actually click restore values and go back and tweak again. So that's the beauty of this and why it is we would do problems like this in Excel. Again, we had a problem. Just to recap, we had a problem with this beam. We wanted to share a bolt on the end. We had a load on one end, and we said that this load must be the lever must be dimensioned such that at 50 kilograms we get a force F2 to fail the bolt. So knowing F2 and knowing F1, we're able to work out a ratio. F2 to F1 is equal to A to B. So that no matter what the length is, A to B, that ratio must be F1 over F2. Right? Or sorry, F2 over F1. Right? And we have unknowns. We don't know the thickness of we don't know the height of it. We don't know A and B. We just have these guidelines of ratios. And what we ask Excel to do is to, okay, let our tau max be equal to our tau design, but at the same time minimize the second moment of area. Also at the same time, we have an additional constraint of deflection, where we said a deflection in the beam must be less than an actual recommended value. Right, so whatever AB is, A plus B, the total length multiplied by the recommended value, which is 0.5 millimeters for every meter. That is our recommended deflection, and our calculated deflection should not cross that. And we could see that we have that happening here. So we're able to get a really nice solution to this problem. Right, so to submit, what you're doing, you're submitting your workings in your Excel sheet. I just click OK here to accept these values. Yes, you can actually paste your calculations right in the Excel window here. That's okay. And submit this.